cooking going. So she's had a number of varied research interests, so generic programming, metaprogramming, machine-assisted reasoning, but in particular, the design and implementation of dependently typed programming languages in the context of the Trellis project. I think these days we're allowed to call Haskell a mainstream programming language, is that right?
Yeah.
I think that's right. So what we're going to hear about today is a bit about the introduction of dependent types into mainstream programming. So please welcome Stephanie Weirich.
Thank you, Edwin. And like Robbie said yesterday, I also would like to thank you and the other ICFP organizers for inviting me. Again, ICFP is my home conference, and it's just such a thrill to be able to give a talk like this here. So, as Edwin said, my interest is in dependent types, and in fact, my goal for right now is to turn all of you into dependently typed programmers. And even let you know what my secret weapon is, right? Haskell. And then you might be thinking, is GHC really a dependently typed programming language? And I want to argue right now that yes, it is. Well, maybe with a few caveats, and we'll get into that. Right? And so, really what I'm going to talk about is the story of dependently typed Haskell, because you can view like the last 10 years as extensions to GHC's type system that make it more and more like a dependently typed programming language. And so I want to go over those extensions in the context of a long-running example throughout the talk and put those extensions in context, compare them to what you might see in what we would consider dependently typed programming languages like Agda or Idris or Cloud. And then I also want to talk about where we need to go next with GHC. So past, present, future, all in one talk. And again, there's going to be stars in this talk, right? I want to set your expectations at the right level at the beginning. So I'm not going to claim that we can take any Clock, Agda, Idris program and translate it to Haskell, to GHC. But what we can do, it's really impressive. And that's what I want to convince you of. Right? And so here's the example that I'm going to use throughout this talk to compare. And what I'm going to do is I'm going to take an implementation of red-black trees in Agda and show exactly how you can translate that implementation to GHC and show you the type system features of GHC that you need to be able to exactly correspond to that Agda implementation. And we're only going to do, so red-black trees are a really great example because they have some invariants that we would like to maintain about them as we write functions over red-black trees. We're going to maintain the height and color invariants. Red-black trees have some invariants that make sure that they are roughly balanced. The fact that you can't have two red nodes in a row. The fact that when you start from the root to any leaf, you have to go through the same number of black nodes. That ensures that red-black trees have efficient running time. We want to write some code, write some types that make sure that our implementation maintains those invariants. Now, of course, you can do more. And to talk about more, I'm going to refer you to Connor's talk later today, where he can talk about how to maintain order invariants. And I will say that a lot of the ideas in Connor's talk, they just directly come over to GHC too. The other thing I want to point out is that I'm going to be showing you a lot of code in this talk, and if you want to follow along, I've put up all of the code from the talk on GitHub. So if you can find my GitHub account, there is a DTH, dependently typed Haskell, repository there. Under that is a place for all the ICFP 14 code. Okay, so red-black trees. And of course, I can't start talking about red-black trees without showing you this beautiful functional Perl from 1993. Chris Okasaki's version of red-black trees, how you implement insertion into a red-black tree in a functional programming language. And this is part of it. I'm missing one bit, but you can see the basics of this implementation, right? We have colors. We have a data type for colors. They're either red or black. We have a data type for trees. They're either empty trees, that's the data constructor E, or they are non-empty trees, right, which somehow used to have a color component. right? So non-empty trees, they have some color, a left subtree, some value, some right subtree. Now I'm not going to really talk about values much in this talk. I'm going to fix that type to be A and not really talk about it much. But one thing we want to do with red-black trees is insert into them. Given some red-black tree and a new value, we want to produce a new red-black tree that is guaranteed to contain that value. And so this is Chris's insertion function, and it's really sweet. It goes down, it finds the right point in the tree to insert the value, the right leaf. It creates a new red node containing the value that you inserted. And when you do that insertion, you have to be careful because you might temporarily suspend that invariant, right? We're creating a new red node. And what happens if we create that new red node underneath another red node? We might be creating two red nodes in a row. And so there's two ways to deal with that, to recover from that potential violation, right? So if it was right up at the top, if the top node was red and then we put a new red node right after that, we have blacken. Blacken just, at the very end, we're going to color the root black. And that's going to recover our invariant that way. If it's some internal node, then we have to rebalance, right? If we have two red nodes in a row, internal in the tree, we can rearrange the tree so that we can recover this, this red-black tree invariant. And I'm not going to show you the code for balance because I think it's a little bit easier to see as a picture. But it really is. It's only 5 lines of pattern matching. 4 different trees that are unbalanced, that violate this red-black tree invariant. 4 different ways that you could have 2 red nodes in a row. And all of them happen to get rebalanced to this tree right here. And then the 5th line of balance, it just leaves all other trees alone. All right, and that's it. That's the code that implements insertion for red-black trees. Right? And I argued to you that, very informally, that this code preserves red-black tree invariance. So if you give it a red-black tree, you get a red-black tree. Do we know that? Do you believe me? Well, Chris is pretty smart. It's probably true, right? Right? But we're gonna prove it. Right? We're gonna do it with types, right? And what we're gonna do is we're going to think about how we could write a type for red-black tree, a new type that captures exactly these level and color invariants. And then we're going to prove, we're going to show that insert has, we're going to find a new version of insert that has this type, that given something that is not just any tree, but a red-black tree, we're going to get a red-black tree out at the end. And so the type checker is going to verify that this code is actually satisfying that is actually preserving the red-black tree invariance. Okay, so we need that type. How are we going to define a type that only contains red-black trees? Right, so we could use AGDA, right? This is a perfect opportunity for dependent types to express such constraints. And here I have some AGDA code that I'm going to work with. I got a lot of this AGDA code from Dan Licata, though I have modified it beyond all recognition for this talk. But so here is an AGDA implementation of a type, and it's going to start off with 2 standard data types. One is just for natural numbers, 0 and successor. One is for colors, red and black are both colors. Right? So that should be fairly familiar to you. But if you're new to dependent types, this is not. So the definition of a tree, now we have a new data type for trees. Before we just had E and T, 2 data constructors to form a tree. Now we have 3 data constructors because we're splitting up when we have internal red nodes and internal black nodes. And the types of these data constructors are going to express the constraints. They're going to talk about the type of tree that they produce. It's going to vary depending on which constructor we use. Right? So trees are indexed by the color at the root of the tree and also the black height. How many nodes there are between the root and the leaf, how many black nodes, right? And so you can see that empty trees, right? Empty trees are black, and there are no internal black nodes in an empty tree. So their black height is 0. Red nodes TR, what does that make? If we go look at its return type, right, we see that it makes a red tree, right? And what's the black height of a red tree? Well, it's the same as the black height of its two subtrees, right? And not only that, those two subtrees, they have to have the same black height. So we're guaranteeing that balancing using these type indices. Black nodes are just the same. The TB constructor creates a black tree, but here we get to increment the black height. It's still requiring that the left and right subtrees have the same black height, but since this is a black node, the resulting black height is 1 more. And now also check out this color invariant. Red trees are forcing the two subtrees, left and right subtrees, to be black, right? We can only have black subtrees under red nodes. Black trees can have any color of subtrees, right? The TB constructor generalizes over any color, C1 and C2 for the left and right subtree for black nodes, right? So here we're using the type to capture these invariants, right? And this is really capturing the essence of how dependent types work, right? So we have all these return types are varying based on the data constructor, right? And the types of these data constructors are dependent types. Here we have the types of these two subtrees for TB. They depend on earlier arguments to this data constructor. That is a dependent type, right? And the other thing I want to point out, you may be wondering why I have these curly braces. That is from AGDA indicating which arguments should be inferred. AGDA does not distinguish between types and terms like Haskell does. And so AGDA type inference is able to infer some arguments. Curly braces and tell AGDA, why did you try to infer those? Okay, so that's our representation of red-black trees in AGDA. What does it look like in GHC? Can we take this definition? This is the same thing from the previous slide. Can we take this definition and turn it into GHC? Right? And the answer is yes. We can actually write something that looks remarkably similar. Right? We have 2 colons instead of 1 colon. But otherwise, it's kind of crazy how similar they look. Right? And what we're using here is we're using 2 extensions that GHC supports. Generalized algebraic data types, GADITs, and also another extension called data type promotion. And now you say, are those really the same thing? Right? Just because they happen to have a lot of characters in common, are they really the same thing? And are they really keeping track of these red-black tree invariants? Well, let me show you how. Let's just play around with this Haskell implementation first, so that first I can convince you that they do actually constrain our trees to be red-black trees. And then I want to talk about the difference between these 2 definitions. Okay, so here we are in GHCI. And we're creating a value that is a red-black tree. It's just a red node with 2 empty leaves, right? And so we give this to GHCI, and GHCI is happy with it. And then we ask for its type in GHCI, and it says, sure, you just made a tree that is red with black height 0, right? There are no internal black nodes in that tree. That's great, right? So these types are statically giving us lots of information. Right? So we can try a little bit more. We can take that tree that we just constructed and put a black node on top of it and ask GHCI if it's happy with this tree. And it is, so we can ask for its type, right? And now we have a black tree, and its black height is 1, right? Because we have one black node in this tree. The height of every path is 1. Now we could try again, where we take our first tree, and instead of putting a black node on top, we put a red node on top. And right, and you notice this is not a red-black tree, right? And this time we get a type error, right? GHCI says, wait a minute, when you try to create that red-black tree, when you use the TR constructor, I was expecting a black tree as that first argument, but you gave me a red tree instead, because red nodes need to have black children. So we are using the type system. It's giving us information about the trees that we are constructing, but more importantly, it's preventing us from creating ill-formed trees. Okay, so let's go back to that distinction. And I showed you they look very similar. And how could they be the same? Because there's this really important difference between AGDA and Haskell, right? So Haskell has a very strong distinction between types and terms. And AGDA does not. AGDA puts everything all together in one syntactic class, right? And in Haskell, that means that types are treated very differently than terms are, right? So what happens to types in Haskell, right? We have type inference, which automatically infers all type arguments. When you have a polymorphic function, we never have to write down how we instantiate it. It's always going to be inferred. We just saw in AGDA, whether something is inferred or not depends on how you specify it, whether you use curly braces. In Haskell, we had this restriction. We have this index type, PADTs, but only types can be the indices. Whereas in AGDA, types, terms, it doesn't matter. They're all the same thing anyway. We have full flexibility about what's in those indices. And then finally, the final distinction is that we know in Haskell, types and only types are erased at runtime. Whereas again, AGDA is not making this distinction. So it doesn't have this built-in notion of erasure. And so let's go back to this. How can we write this type for trees? But it looks a lot like we are indexing this type by terms. But really we're not, right? Because what we're doing, we're taking advantage of this extension called data type promotion. And what data type promotion is, it's extending our type language so that it has stuff in it that we would expect from the term language. So with data type promotion, when we define a data type like color, right? We say color is either red or black. If we have data type promotion enabled, that means we're at the same time also defining a data kind. And we're defining both red and black as constructors in the term language and as constructors in the type language. And there's not really much connection between the constructor R in the term language and the constructor R in the type language. They just happen to have the same name and the same structure. But since it's available in the type language now, we can use it for indexing. And we can use it in cases like this tree where we want to index our red-black tree with colors and actual numbers. And then the other difference that I mentioned is that types are erased in Haskell. And so what does that mean when we're using them as indices for GADTs? So here's a difference between AGDA and Haskell. So we defined that tree type, but remember that insertion function, it actually wanted a top-level type for red-black trees, right? Internally, when we define insertion, we'll need to define it as a recursive function over the tree type. But the top-level type should be a well-formed red-black tree with a black node at the root. That's one of the invariants of red-black trees, is they start with black. Right? And so to define that top-level red-black tree, right, we can give these two definitions in AGDA and Haskell. And again, they look very similar. Right? A red-black tree is a tree that's black in the root. And then we also don't really care what its black height is, so we can hide that in our type definition. But there's one big difference between these two definitions, which is we're hiding that type, that height. In AGDA, we can always get that height back, right? That height is just a natural number. We're indexing our trees by values, and so we can project it out of our type, this RBT type that we've just defined. In Haskell, we can't do that. In Haskell, we're hiding a type this time, and you can't write a function in Haskell that takes a value and returns a type, right? And then the reason you can't do that is because types are erased. What would this, since types are erased, what would this black height function return? Okay, so I showed you how to represent red-black trees. Let me spend a few minutes talking a little bit about history. Where do these features come from? How do we get to them? So I'll first start with data type promotion, and that's a fairly recent extension and something that I thought was a pretty straightforward extension, right? The idea was that we wanted to index data types like GADTs with things that look like they're from the term language. And so what we'll do is we'll make a copy of the term language in the type language. And as we were doing that, we realized that we probably wanted to make the type language a little bit more expressive. We wanted to have kind polymorphism. Because you have things like cons, which is a data constructor with a polymorphic type. When we promoted it up, we wanted it to be a data constructor with a polymorphic kind. Right? And this turned out to work beautifully. Right? There was only one little snag, which was as we were doing the promotion, we found it was very easy to promote things that were just from polymorphic functional programming. We couldn't promote anything that was indexed. So we couldn't promote GADTs. And that's because the core language of Haskell just had no way to talk about this. So it was easy to promote things like cons, but there is this limitation that you can't promote things like tree to the type language. And I'll get back to what that limitation actually means. GADTs, on the other hand, have a much longer history, right? So they've been in GHC for almost 10 years now, and when they came about, there were many people working on how you might take this idea of index types from dependently typed languages or just from crazy type encodings and add them to mainstream languages like Haskell, right? And so we were some of many people that we all had different names for what these things were, and we were thinking about how we might put them into the languages that we know and love, right? And the real challenge was from the integration with type inference. So GHC has Hindley-Milner type inference. That was just this really sweet spot in the world of how to specify when things type check. And extending it has always proved challenging, trying to make it more expressive than its original definition. And the last thing I want to note is that GADTs are about 10 years old, and they could have been 20 years old, right? So as we were working on GADTs, we got, Leonard gave us a copy of this paper that he had written. Right, so here in Gothenburg, GADTs were invented 20 years ago, right? And so what I'm putting this up as, don't throw your ideas away, right? It's hard when you're doing research to know what is a good idea. This was a good idea. It wasn't silly. Okay, back to red-black trees, right? So I told you we were gonna talk about how to do dependently typed programming, and I've done the first step, right? If you remember Norman's design process from his talk, the first step was, well, one of the early steps was to think about the types of your data, and then you start to think about the types of your functions, and then try to think about how you might implement those functions, right? And so we need to think about how balancing works. And so if you remember, in our insertion functions, we want to implement insertion and show that it preserves red-black trees. And we have a little problem, right? Because when we're doing balancing, what's the type of this guy? We just made a type that only contains valid red-black trees. And this doesn't fit in our type. If we tried to make this tree, Haskell would say no. GHC would reject that tree. So what are we going to do about it? Right? And so what we're going to do is we need to define a new type that's just going to be to represent the type of that argument of balance. And before we do that, I kind of want to break the operation of balance up just to simplify our life, just to make the type that we have to define a little bit easier. Right? So if you remember, balance took 4 different trees and rebalanced them. I'm just going to split its operation in half, based on whether the invalid tree was caused by a recursive call to insert on the left subtree, and whether the invalid tree was caused by a recursive call to insert on the right subtree, right? And these two functions, I'm going to call them balance left balance right, they're symmetric functions, right? And so I'm just going to focus on now balance left. How can we implement balance left? But now we really only have 2 invalid trees to think about, right? So we want to take balance left that takes an invalid tree like that and balances for it. And now since we know that the invalid tree is only going to be on the left side, we can kind of decompose this argument and break it up into pieces, right? And so we can take that tree there and split up its root, its left child, and its right child, and have balance left take 3 arguments instead of 1 argument. I'm not showing the value, but because I really want to focus on the structure of the tree. Okay, and what we've gained by doing this, by decomposing that 1 tree into its 3 components, is now we have a really simple type here. This left subtree, it's violating the invariant, but it's really violating that red-black tree invariant in a simple way. Only at the top could you have a red-red in a row. Every other part of that type is a valid red-black tree. Right? All of these gray triangles, they are valid red-black trees. And then I'm going to do one last thing, which is specialize balance left to when we're balancing after insertion into a black tree. So we've inserted into a black tree, so we need to rebalance when that first argument is black. And so I'm going to talk about a version of balance left that works when that first argument is black. And I'm going to call this one balance left black. And it has an implicit black as its first argument. Okay, so balance left black. This is what it needs to do. There's actually 3 cases for what balance left black has to do. We have the 2 unbalanced trees, and then we have where that first argument is a fine tree. We don't have to do anything. Every single case we have to construct a new tree from it. What's the type of this function? You can kind of see, right, we have the left tree, we have the value in the middle that we're going to need to construct the result tree, and then we have the right subtree. But what's the type of the thing that we get, and what's the type of the thing that we're sending to it? Right, so let's look at this type. Right, what's the result type? Right, we're making valid trees. So it might be nice if we could use tree, but we can't use tree directly. And the reason we can't use tree directly is we don't really know what color of tree, right? And remember, tree always talks about what its color is, right? And sometimes we're getting red trees, and sometimes we're getting black trees. And so what we really need is a type that is, it's a valid tree. We know it's even a non-empty tree, because we just did an insertion. It's not an empty tree, but we just don't know what color it is. So I'm going to call this type hidden tree, and then we'll talk about how we can define it. This type over here, though, right here we have to talk about violations, right? And so here, again, we need a non-empty tree, but it may break the color invariant at the root. And so this type I'm going to call almost tree. It's almost a red-black tree. It could have that red-red violation right up to the root. Right, so let's think about how in AGDA we could define those types. Right, so here's our hidden tree. Again, it's a non-empty tree that's completely valid. We just don't know what the color is. And by saying we don't know what the color is, we're not going to index this type by its color. And now how do we represent that it's non-empty? Well, there's 2 ways that red-black trees can be non-empty. They can be red, because red trees are not leaves. Or they can be black, where the black height is at least 1. Right, because the leaf, that E constructor, that is a black node of height 0. And that won't fit as either of those trees. Right, so we have hidden trees. What about non-empty trees that can break the color invariant? Right, so for that definition, I'm going to use this one. So this is almost tree. And here I'm going to be really clever and talk about almost tree, both kinds of. So almost tree, it could have black at the top, it could have red at the top, right? It could be some tree where you have a color, you have a left subtree, you have a value, you have a right subtree, it's non-empty. But we're going to have one constructor for both black and red, right? We don't need to have that relationship between the color and the colors of these two subtrees. They can be anything. So that's going to allow us to have that violation. We can have red here as the color of this node, and then we could still have red on either one of those. We're not going to track that. But we still want to keep track of the height. And to keep track of the height of this tree, we're going to have a little function that's going to calculate whether we need to increment the black height in this case. So if this color happens to be black, we want the height to be incremented. If the color is red, we don't. Right? And so here we're using dependent types. We have some color and we have a function written over that color to help us figure out what the right type of this tree is. Okay, so we've defined, that's the type. We wanted to say for balance left black, we're going to take something that's almost a tree. It might have an invariant. We're going to take something that is a tree, and we're going to produce something that is a tree. We just don't statically know what color we're getting. Right? And so what cases do we need? Right? So we need the two balance cases, and you don't really need to look too close. These pattern matching, it's identifying a tree that looks exactly like this according to those types and rearranging it so it looks like this for those two cases, when the red is over here and when the red is over here. And then we have three more cases for when we don't need to rearrange the tree. And this is a little bit different from Okasaki's version. Right? So in Okasaki's version, he just needed one pattern match that just kind of caught everything and said, if none of the previous cases match, just leave the tree alone. Here we can't do that. We've given a really strong specification. Here we actually still need to pattern match because the proof in each of these cases that we're producing a valid tree is different in each case. Right? We're getting something that potentially could be a violation, and so we have to pattern match to prove that it's not a violation and that we can just leave it alone and it will be fine. Okay, now we have to do it in GHC. But, well, you know, it looks very similar, right? So I'm not going to talk about hidden tree because it translates exactly, but I am going to talk about almost tree. How do we represent almost tree in GHC, right? And so almost tree, it looks very similar in GHC. We have, and there's two things I want to point out. Right? So if you remember in the active version, we had a function that calculated the black height in the result type of almost tree. Here we can't really just use a function directly. We have to use something from the type language. But this is what type families are for. We can use a type family to express the relationship, to express whether we should be incrementing this natural number or not based on the color of the tree. So here's our type family that captures that increment function. The other thing is that we have this type term separation. Remember, we have this erasure property. And if you remember on the code for balance, we needed to look at the color that was the argument to almost tree to figure out whether we needed to rebalance or not. In Haskell, that color is a type index. It's not available at runtime. So we need some way to get a hold of it to figure out what color of tree we have at runtime. And so for that, we're going to use this singleton type. So a singleton type is a way of using a GADT to create a constraint between some type level data and some runtime data. So the singleton type, so it's called a singleton type. I mean, it's a little confusing. There's two constructors there. But if you look real closely, you'll see that if you look at the type sing_r, there's only one non-bottom element of sing_r. That is SR. And SV is the only non-bottom element of sing_b. And if you have something that has type sing_c, where c is some type variable, and you pattern match on it, you can find out what c is. Because if it turns out it's SR, then it must be that that variable was R. And if it was SV, then that color was black. Right? And so that's going to give us the handle that we need to be able to write that rebalancing function. Right? So let me talk a little bit about singleton types. So singleton types are a very old idea, and I'm not being nearly complete enough. They've been used many, many times be able to, when you have a language that separates the indices of index types from the normal expression languages, singleton types are your trick for reestablishing that connection, for being able to make some runtime choices, learn information at runtime about your index type, right? And what's really nice about it is we even have a proof that you can take a dependent function type, like an AGDA, and translate it to a language that doesn't have real pi types, that is just going to model pi types with parametric polymorphism and singletons. And if you have enough expressiveness in your target language, you can get an exact translation. Now in Haskell, we don't quite have enough expressiveness to capture all of AGDA. Again, I said we can't do everything. The fact that we can't promote GADTs means there are certain kinds of programs that we just can't write. Right. But we do have the singletons library, which is some template Haskell that can help you, if you are writing dependently typed code, help you automatically do this translation in certain cases. Though I will warn that once you start programming with a lot of singletons, it can get rather unpleasant, as Connor's Haskellism paper pointed out last year. Okay, type families, that's how we represented that function at the type level, right? That's trying to capture this idea that when we write types, we might want to actually express functional relationships to them, right? And in GHC, they've been around for a long time, and again, a lot of the challenge with adding these type level functions has been in the integration with type inference, but they are really expressive, not just independently typed programming, but also in terms of generic programming and giving just very flexible interfaces to libraries. And so I want to spend a little bit of time talking about how they're different from the type functions that you see in AGDA, right? And so type families, they look, that anchor looked a lot like what I wrote in AGDA, right? But I was actually really fortunate that I didn't, for example, try to use an anonymous function. So here we are trying to put functional programming in our types, but we don't even have lambda. So that's one restriction, right? And another restriction is that they're not really very higher order either. Every time you have a type family, you have to give it all of its arguments. You can't pass it in, you can't do partial application, you can't pass it in as an argument somewhere else. So here's something that I would love to be able to do: define the identity type function and make it an instance of the monad type class. No. No. But you just, right. And there are also restrictions on how unification works in GHC. It's actually rather brutal, right? Because GHC doesn't really do any reasoning about whether the type family is injective, and since we don't really know whether it's injective or not, you basically have to assume the worst. And so things that look like they very much should type check just don't. On the other hand, there are ways that type families are more expressive than functions in AGDA, right? And for example, that you can't write a function in AGDA that pattern matches against a type, against something that has type set. Right? Set is this opaque thing. In Haskell, you can take it apart. And that is really useful for those flexible interfaces. And the other thing, once we have with closed type families, you can also write things like this, a polymorphic equality function at the type level. This is a type level function that determines whether two types unify and reduces if they do, reduces to true if they do, and to false if they don't. It's allowing the type level to observe unification. And that's really useful. If you were at WGP, Patrick Barr gave a really beautiful presentation about how he could use this capability to have a nicer version of data types all the time. Okay, so back to our balance code. Right, so this is the code that I just showed you before in AGDA. Right, what we did is we rewrote these types, almost tree and hidden tree, in Haskell. And here's the AGDA code that uses those types. What does the Haskell code look like? right? Things are a little bit different, but the Haskell code is really similar. Like the only change that we did, we had to have some singletons around, so I made all of those arguments to almost treat the singletons. That's it. Oh, I added another couple. Right, and so it's great, right? So I showed you for balance, you can kind of keep on going, finish up the job. You can take that AGDA code and get a Haskell version that is just in lockstep, line by line, almost the same. But are they really the same? Right, so here, you finish it out, you get these types for insert. The type checker verifies that insert is taking binary search tree, a new value, and give you a new binary search tree. Are they really the same? Have we done the same thing? And we write this in AGDA and Haskell. Well, what do these types mean? Right, in AGDA, the type means this, that if you're given this valid red black tree, you will produce a valid red black tree. In Haskell, it's slightly different. In Haskell, it says, if you get a tree at the end, it's going to be a valid red black tree. Haskell's not promising totality. It's not promising that insert is always going to give you a red black tree. It could fail, right? It could run forever. It could have a pattern match failure, right? So totality is a really big difference between AGDA and Haskell, for better and for worse, right? So in AGDA, we know more about that implementation, but also in AGDA, we have to prove everything total, right? We don't get the chance to ignore totality if we want to. And sometimes, if we're ignoring totality, we could simplify our reasoning. We could do less work for less payoff. That's kind of a good thing, to have the flexibility to do less work. Right? And in this example, I've noticed that if we ignore totality, we can actually produce a simpler version of insertion that you can't really write it in AGDA because you can't directly prove that it's total. But it's a little bit simpler than the one that I just was presenting to you. And the difference between these two versions is that the Haskell version that ignores totality, it's a little less precise in the types, right? Right, so we worked out the type of balance left black, took an almost tree and a tree, and it actually did balance it, so it produced a hidden tree. If we worked through, we also looked at balance left right, or red, the red nodes, that you don't have to do any rebalancing, but you don't know if you get something that doesn't have two red nodes in a row. So you end up with those two types. You can kind of combine them together. So instead of having this hidden tree, which is it's a fairly strong type. It says you've done what you needed to do, you just don't know statically what color it is. If you relax that a little bit, you can combine balance left black and balance left red together again into just one function and just use almost tree in every case. And here you get a version that's closer to Chris Okasaki's simply typed version. It's a little bit closer because it's not splitting up these different colors, and it's a little bit simpler because we can just reuse balance everywhere. But there's no way AGDA, it's not precise enough to do the totality reasoning. It can show, it's precise enough to show that we preserve the color invariance, but it's not precise enough for totality. Okay, so what's next? Right, so we had those stars, right? I showed you something that we can do, right? But again, this restriction on data type promotion, it really does mean that there are some AGDA programs out there that you just cannot write, right? And the reason is that our type language is basically polymorphic lambda calculus. We have the trick once. We can do dependently typed programming between the term language and the type language, but once we get into the static reasoning, we can only do polymorphic lambda calculus programming, right? But so I and mostly Richard are working together on a way of extending GHC so that we can have dependently typed programming in the type language. Right? And so last year we talked about how we could extend the core language. Richard has gone and implemented that. He's working on the really gnarly problems of type inference. He's going to give a talk about it at the Haskell Implementers Workshop if you want to see his work in progress. Right? So that was one thing, was data type promotion. It really limits what we can write. Another restriction that we have is that this issue with the singletons that we had to, that once you start using singletons a lot, here we were lucky, there were only a few places we needed to use singletons, they were relatively benign, but sometimes having a lot of singletons around can just be a real pain. And so for that, we actually have a roadmap of what to do, and it seems very doable. So I really want to point out Adam Gundry's dissertation for describing how you can look at Haskell, think about what in the type language is shared between the types and the terms, where are they the same, and how do we introduce a new quantifier over those guys. Okay, so that's currently in progress, and that's work that we are doing to get rid of that star. But what else do we want? What else is on my wish list for dependently typed Haskell? Yeah. Sure, yeah. After I've solved 2 impossible problems before breakfast, what next? Right? Well, TDD, right? Right? And by TDD, of course, I mean type-driven development. Right? And so what do I mean by type-driven development? Norman talked about this a lot in his talk, about a systematic approach to program development where you use the types to guide you to your program. And once you have dependent types, that just levels up type-driven development. Right? That levels up your game. Right? And so here, I found this great post on the AGDA mailing list about an AGDA implementation of red-black trees. Right? And this one was much more complete than the one I showed you. Not only did it do the color and level invariants, it also proved the ordering and the fact that they were implementing sets. But the really interesting part of the quote is down at the end, where he's like, I'd never done this before. I'd never implemented delete for red-black trees, which, by the way, is really challenging. But he just used the types. He expressed the properties of delete that he wanted to, and he used the types to help guide him through his implementation. He had an idea of what deletion kind of had to do, but the types really drove home how to implement it. And that's the experience I want to have in GHD. Right? We're not there yet. Right? So my wish list, right? Maybe the ICFP 2015 program. My challenge to you, right, is to think about this. How can we have more type-driven development, right? So, yeah, we don't have totality checking in GHD, but we really need more totality checking. And not just termination, but pattern match coverage, right? We just have to be a little bit better about that. Right? And again, GHD is awesome with type inference, but it's also frustrating with type inference. Right? It's great that we have lots of properties about the Hindley-Milner type system, but that does lead to limitations like how we can use type families. Can we think about the trade-offs? What properties do we lose? What properties can we retain if we try to extend type inference? And how can we go and take special kinds of constraint solvers? GHC has written type inference as a constraint solving problem. Perhaps we can have some special purpose constraint solving just for dependently typed programming. And here I want to point out Javor's type nats extension, where he's putting in literals and natural numbers, and he wants to reason about arithmetic at the type level. Can we plug in some architecture for that? And then error messages. I mean, we all complain about error messages, but I want to ask the question in the right way. Is there a way that we can design the language so that when you're writing your code, you can make it give you better error messages? Is there a way we can program the error messages? I don't know. It's really fuzzy, but maybe there's some way we can do better here. And then finally, IDE support. Once we have types, right, we want to use them while we're developing. If we're doing type-driven development, we want the IDE to help us. And we saw a lot of this great stuff in Ulf's keynote address last year when he showed you just what Emacs could do when you're programming with AGDA. I'd like to be able to do that with GHC too. Okay, so conclusion, we could use dependent types in GHC with some limitations that we're working on, but I really want to get to that future where we can use the dependent types to really drive our program development and really extend what we're able to do in GHC. And I want to end with just a thanks to a lot of people, collaborators and people I've talked to about Red Black Trees, National Science Foundation. Thanks.
Takayuki Mayoshi from Kobe, and I'm just curious about one property that you have been missing. And I actually saw it in the email you presented.
Yes.
The sortedness. Is that difficult in GHC because it has to deal with the values in the tree?
Yes and no, right? So if you're working with values that you can reflect with singletons up to the type level, then you can reason about sortedness.
Even if those values are given at runtime from files and so on?
Yeah, even if they're given from runtime, at runtime, right? If you have a way, because again, with singletons, you have this double abstraction going along, right? There's some runtime value, it has some type, but I'm polymorphic over that type. So I don't really need to know exactly what it is. I have a variable representing it. So even if you get it from runtime, you can still give it a precise but unknown type.
Can you compare singletons based on the value level or the instance?
You need to have a singleton alternative to org that gives you more information when you compare the runtime values, right? When you compare things with singletons, you also need some information at a type level about that ordering. And again, I want to point actually to here. Under here, so ICFP 14 has the examples from this talk. It also has some other examples of dependently typed programming, including some Haskell equivalents of what Connor is going to talk about. And I can, if you look around, you'll find that.
Let me look around. Thank you.
Andrew Kennedy from Microsoft Research Cambridge. Very nice talk, Stephanie. I have a couple of questions. One's just a bit of a technical one on your implementation of web batteries. Do you have the slide with the data types?
Sure.
I'll have a long way back.
Which type are you looking for? The top
the
level?
hidden tree and the other one.
Oh, the hidden tree.
Is it hidden tree?
So this one? This is the active version.
Okay, so why don't you use the incra function in the definition of hidden tree to avoid having two constructors? It looks like.
Yeah, you could do that too, right?
Okay.
Again, with all of these implementations, there are many ways that you can do it. What I'm showing you here is not exactly the way that Dan did it in the code he gave me, but I was doing it for the purposes of building up in this development, in this talk.
Okay.
So there are many alternatives. There is one alternative I should point out, which is you could even use incr in your top level definition of tree. So if you remember, in our definition of tree, we had different TR and TB. We could even combine it there with incr, but only in Haskell, right? With balancing, the pattern matching interferes with that incr function, and I couldn't figure out how to get that to work out.
Okay. So the second question is more general, I guess, probably about dependent types. But so you've had to change the algorithm that Okazaki gave, possibly with more computational cost. Is that a general issue? I mean, can you take an algorithm like Okazaki's and add sufficient refinement using dependent types, or do you typically have to create new data types with in order to get the invariance expressed as you want?
Yeah. So here, like, it's not clear how much the cost is. Like, we've made new data types, but there are intermediate structures that we would have created anyway. And whether we use tree or we use almost tree for that intermediate structure before we rebalance, I don't think that's going to change the cost. The real change in cost is we did a little bit more pattern matching than we normally would have when we didn't need to rebalance the tree, right? Perhaps we had to do some more work there. Now, there is a solution which is, so what I was showing you based on AGDA is internal verification, where we're taking our data types and we're adding information to them so that as we write the program, we also get the proof. You can also do external verification, where first you write the program and then you verify afterwards. And Haskell is much worse at that than for example, Coq is. You could do it, it's really crazy singletons. You don't want to see it. But also, you also don't have anything for like the type-driven development, right? You don't, it's not mixed into your data structures, so the types can't help you come up with that algorithm. And so that's the other reason I wanted to show it in the internal side.
Okay, thanks.
I have a short comment on the question. The comment is that as I'm writing how to design programs, which is untyped language completely type-driven development, I've often found myself thinking dependent types. But that's not enough to do a design philosophy. So I challenge you, this is just a comment, so to think about how to put this into this design process that we have wrapped around these ideas. Here's the question, keep it separate. Are dependent types infectious?
Are they infectious? That's a great question, right? So once you start using dependent types, you have to use them everywhere, right? So
I'm expecting the answer to be no.
yeah. So here, we'll go back to my example with red-black trees, right? Once you've implemented red-black trees with these dependent types, you can give them a set interface that doesn't say anything about them, right? You don't have to use them with the dependent types, right? You can use them with a much weaker interface, just lay it on top. Of course, maybe you want to reason about other parts of your program, and that reasoning depends on knowing the correctness of your set implementation. And in that case, it would be infectious.
So infectious would mean it's gradually penetrating the program, and you don't have to rewrite the whole program.
Yes.
But I'm afraid, so that's the subtle part of the no.
Yes.
The subtle part is probably that you are forced to rewrite the entire program unless you superimpose this weaker interface.
What is a whole program?
A whole module.
Right. I mean, if you're reasoning about red-black trees, right? That's a bunch of reasoning about the entire system, right?
No,
so,
yeah, I really meant your clients, for example.
Oh yeah, your clients, right? Yeah. So you have to choose your interfaces carefully. Yes.
So it's not infectious. It's in its gradual sense. It's a force. It's a brutal force on the rest of the program.
We put on interfaces all the time.
Okay, very nice presentation. So I was wondering, so at the end you sort of mentioned termination, and so there are like a number of kind of very different points in that space, some of which involve syntactic checking, others involve actual proof, and sometimes it's optional, sometimes it's not. So I wondered if you could talk a little bit about where you landed with respect to trellis, and if you think that those techniques are applicable to Haskell.
That's a hard question, right? So, so the trellis project, if you don't know about it, was looking at a new dependently typed language that allowed you to have optional termination checking. And so the types actually keep track of which part of your program is written in the terminating fragmented language and which part of the program is more like Haskell, does not guarantee any termination, right? And the question is whether we could take the ideas, the type structure from that system and bring them over to Haskell, right? And yes, with a lot of work, but there's a lot of work in sort of showing that the type structures that guarantee termination in trellis would actually continue to guarantee termination in Haskell, right? And that's where the real challenge is.
Thank you.
Phil Wadler, University of Edinburgh. So I want to thank you for a lovely talk. That was really great. But I'm not sure whether I should be thanking you for making Haskell more complicated.
You are not welcome.
So the question is, to what extent is this research best carried forward by saying, right, here I am working on trellis, I'm going to try out these ideas, and to what extent is it best carried forward by saying, here, I'm going to put in this mainstream language, Haskell, which takes a lot of work, possibly opens up these ideas, and I guess particularly I want to ask, is there then a stream of ideas coming back from putting it in Haskell that feeds that into the other work? If there is, that's a clear reason for doing it. If not, maybe you should be leaving us poor Haskell programmers alone and working out how trellis goes.
So clearly, I think you should do both, right? Because that's what I have been doing, right? And I think you should do both because I think you Haskell programmers want it. So maybe you're not.
We suffer from Haskism.
But and the other sense is that there is a certain kind of information that you can get only at scale once you are doing this research in the context